please be seated. A lovely afternoon to everyone who's present here. I know so many of you have turned up, particularly for Professor Rosman. I want to extend a really warm welcome to members who've joined us online, but particularly to you, Professor Rosman, and your extended family. I know what pride everyone takes in being here. To yourself, I'm really sorry about this. I should have put this off. I thought I did. And if I can find it, and I can't find it, so that's the other thing. I'll start from scratch again, Benji. It's the robe. It's really the robe that I don't like. Benji, while the joke's on me, I should make one of you. I bet you wanted to come with your shorts and your father said no. So that's me. My name is Ruxana Osman. I'm the Senior Deputy Vice Chancellor presiding over this wonderful event. And the event is really to celebrate Professor Rosman's professorship, and it's an opportunity for him to do an inaugural lecture today. So let me extend a very warm welcome to Dr. Rosman, Kevin Rosman, and his extended family. Welcome to Wits University. I want to extend a welcome to you, Professor Chetty, as the Dean of the Faculty of Humanities. I'm from humanities, so I expect everyone to be from humanities. And I could hear Richard booing you a little bit, but from the Faculty of Science. And then Professor Klein, thank you very much for standing in for your head of school. I do want to acknowledge the former chair of council, Justice Cameron, who's here somewhere in the audience. I thought I saw you. There you are. You're very welcome back to Wits University. And of course, I'll take you to the side and ask you, so how is Stellenbosch similar to us or different to us? So expect that at the end of the session. I also really want to extend a welcome to many students who've joined here to listen to Benji, staff members, colleagues, and of course, many, many collaborators. So a really warm welcome to everyone who's here on a really hot afternoon in the Senate room. The proceedings for this evening are very straightforward. I hand over to the Dean of Science, who will preside over the evening, and then we'll ask you, Dr. Kevin Rosman, to do a vote of thanks. So warm welcome to Wits University.
Thank you, Prof. Osman. Yes, the Faculty of Humanities, I consider that a bit of a promotion. Madam Senior Deputy Vice Chancellor, Professor Ruxana Osman. It is my pleasure to present Professor Benjamin Rosman from the School of Computer Science and Applied Mathematics in the Faculty of Science to deliver his inaugural lecture on the topic of assembling knowledge, a tale of intelligent machines and research communities. Now, Professor Benjamin Rosman runs the Robotics, Autonomous Intelligence and Learning Laboratory in the Faculty of Science and is also the director of the National eScience Postgraduate Teaching and Training Platform, one of those horrible acronyms, Prof. Osman, NEPTTP is what we call it. He's also the Chief Science Officer of Lelapa AI, building AI for Africans by Africans. Wonderful innovations there. Prof. Osman received his PhD in informatics in 2014 and previously obtained his master's degree in artificial intelligence, both from the University of Edinburgh. He also has a BSc Honours in Computer Science and a BSc Honours in Applied Mathematics, both from WITS. His research interests focus primarily on reinforcement learning and decision-making in autonomous systems, specifically on how learning can be accelerated through abstracting and generalizing knowledge gained from solving related problems. He's a founder and organizer of the Deep Learning Indaba Machine Learning Summer School with a focus on strengthening African machine learning, which now has satellite events in over 35 African countries. He was made a 2022 CIFAR Ezeli Global Scholar by the Canadian Institute for Advanced Research in Learning in Machines and Brains, was the 2017 recipient of a Google Faculty Research Award in Machine Learning, and a 2021 recipient of a Google Africa Research Award. In 2020, he was made a senior member of the IEEE, which is quite a laudable accomplishment. He's an advisory committee member of the Reinforcement Learning Conference, a member of the AAAI Membership Committee, a member of the IEEE Cognitive and Developmental Systems Technical Committee, and a member of the Scientific Committee of Association of AI Ethicists. He has over 100 publications in machine learning related topics, largely in top-tiered international journals. He has supervised a combination of over 70 master's and PhD students during his rather young career, I should add, and reviewed papers for 75 journals and conferences. Has given over 150 academic, corporate, and public talks around the world. Ladies and gentlemen, as you well know, artificial intelligence is suddenly practically everywhere and will increasingly become integrated into society in the coming years. As this happens, these machines will shift from being conversational partners to acting in the world, requiring them to learn to achieve complex goals, a particularly difficult challenge. As humans, we are good at assembling our previously acquired knowledge to tackle different problems. In this talk, Professor Rosman will discuss how reusing and combining different pieces of behavioral knowledge can also enable machines to solve novel problems. It is not enough to build better machine learning frameworks. It is also critical that different communities possess the relevant expertise to adapt AI to their local context. This is where the humanities comes into play, Professor Osman, so you were jumping ahead here. His dream is that the combination of increasingly capable machines and growing communities will pave the way to a bright future. Madam Senior Deputy Vice Chancellor, I present to you Professor Benjamin Rosman for his inaugural address.
Hi everyone, thanks so much for coming out. I really, really appreciate it. There's a lot of you today, so no pressure. Also, for those of you who know me, I'm normally comfortable wandering around in shorts, so it would be a deliciously hot day today to just make this extra uncomfortable. But enjoy this. This will be like probably the only time you'll see me wearing a tie on campus. Really, thanks everyone for coming out and joining. This is an absolute honor to be here and address you today. And yeah, I guess tell you a little bit about me and my journey and what I happen to find interesting. So, before I was born, I had a stroke. And you can see a relatively recent image of my brain scan over there. But this was a bit of a challenge to start life off. And my poor parents, they didn't know if I was going to be able to walk or talk or feed myself or anything like that. They weren't sure if I'd be able to go to a normal school. And one of the doctors reassured them that they knew someone with a similar condition who'd managed to finish matric. And so my poor parents had to struggle with all this uncertainty that I brought to them from right at the beginning. And I'm sorry that I disappointed them and finished school. But it was really with a lot of care and love, and I guess a lot of physio as well, that I started working through this. Turns out I had cerebral palsy, which left me with a right-sided hemiplegia. So what this means is that I have very little to no fine motor control on the right side of my body. So I had to walk around, as you see there, with a splint on my leg for many years and on my hand as well, and destroyed all my hopes and dreams of becoming the next great sports star. No. But fortunately, I had a very loving family and a very kind and considerate brother who could help me with the things like kicking a ball straight, which were and still are completely beyond me. So, not being able to turn to sports, I had to find something else to keep myself busy. And fortunately, we were lucky enough early on to have a computer at home. And this was something that I really took to. Like, this is something I could work with. I didn't need to have lots of dexterous motion in 2 hands and legs. I could figure out something to do here. And so I really took to computers, and I particularly took to programming, and specifically game programming. I decided I was going to become a game programmer. That was my calling in life. So I spent a lot of time, all my evenings and weekends, hacking away at this and coming up with new things. I was quite excited. I managed to find last night one of these still worked. This was an early one I did, I think probably in late primary school, where I decided I was going to make my own 3D engine. And so I had to learn a couple things to do that. I had to learn about something called trigonometry, and I had to learn about something called matrix algebra. I was very confused and went to go ask my teachers, and they were equally confused. But I found a way to work through this, and yes, games were going to become my thing. I was building these games, these 3D engines. This was my calling. So fortunately, my very wise parents convinced me that the correct way forward here was to study computer science, and I should come to Wits to do that. And I've been a proud Witsie ever since. So I was doing computer science. I found a few other things that were interesting. Fortunately, I had a lot of help from people, including now a close colleague of mine, Pravesh, who famously helped me choose my subjects that I was worried about choosing. And so I ended up double majoring in computer science and applied maths. And because these were both very cool, I didn't know what to do with both of them. Obviously, I was still going to make games. There were no questions about that. But I had to find some way of combining these, but that wasn't quite happening. So instead, I just went and did an honors in both of them over 18 months, which was a terrible idea. I don't recommend that. But while I was going through this journey, there were all sorts of exciting things happening around me. And a really important moment was when one of my lecturers, Sarah, invited me to work on a paper with her. This was in my second year. And I worked on this paper that had been started a few years before, and we ended up publishing it. It was published, my very first paper, kind of going from second year into third year, helping with a bit of the data analysis. That was really exciting. That gave me a taste for what doing research could be all about. And we look at the other authors on this paper. Professor Ian Sanders would, in my computer science honors, be my honors supervisor. And I would work on things that I guess these days we'd call image processing or computer vision. There was this other co-author, George. And I never met George. He was some student who'd been around a few years before and had then subsequently moved overseas. And turns out we discover many years later that we have all the same interests, and we've now co-supervised many students together. He's a professor at Brown University. We've started a company together, and all sorts of interesting things just came out of this first paper. So anyway, I did my degree, I did my honors, struggled through that. I mean, just to show you, we had a bit of a reunion of our computer science honors class. That's 80% of the computer science honors class. It was slightly less popular than it is now. So, anyway, I was moving on to do the game design thing. But along the way, I discovered, maybe there's some other stuff here that's quite cool and quite interesting. And I decided maybe a master's would be a good idea. And I ended up moving to Edinburgh to do my MSc. And when I was there, I was absolutely amazed. And see, I'm even wearing the tie of that today. I was amazed that they had all these options. I could do things like robotics and AI and machine learning, and I didn't even know what these were, except they were things that I saw in sci-fi movies. And so I just sat down. I remember sitting down one day with this list of these subjects, thinking, "Oi, how can I do all of them? That would be awesome." No, I couldn't. But I did decide then that my philosophy was, I'm going to make sure I always do the coolest things that I possibly can, which I've amended over the years to now be do the coolest things I possibly can with the coolest people that I can. So I was very lucky that I managed to get some funding from the Sky Foundation to do this, which really opened some doors to me. I wouldn't have been able to study abroad without that. And during my master's, I took a course in robotics, obviously, because it was cool. And this was taught by Dr. Subramanian Ramamurthy. And this was a fascinating course because everything I'd basically ever learned in computer science and applied maths just appeared in this course. I thought this was so cool. I never thought that I'd have it all coming together like I had a plan all along, which I totally did. But I really, really loved this course, and I ended up doing my master's with him as my supervisor. And he really had a profound impact on me. He became a mentor. We had many, many discussions about all sorts of philosophies and plans and opportunities. And then I decided, actually, I want to stay here and do my PhD. I was considering going abroad somewhere else, maybe in the US. But I thought, really, this alignment was just working for me. These were the kinds of projects, the kinds of people I really wanted to work with. And so I decided to stay there, and I joined the lab. He really became a mentor to me. This is a picture. We were the first team in the UK to enter RoboCup, which is the Robot Football League. And this was quite funny because we now have a team here at WITS as well, a number of years later. But so I started dabbling more and more in robotics. The core work that I was in is this area that we call reinforcement learning, which is kind of an intersection of machine learning, decision making, with a bit of robotics thrown in for fun. It was a very niche area back then, but it brought out, I don't know, the poetic side. So I spent my time there doing my PhD, and by the end of it, I could graduate in true Scottish style. Now, my PhD had been partially funded by the CSIR. I'd applied for a scholarship, and I made it to the final round, and I was very upset that I didn't get the funding that I wanted, which would have covered my PhD. But during these discussions, in all the panels and the interviews and so on, I met several people from the CSIR based in Pretoria, and they were just amazing people, really exciting, and they came in and made me an offer that they were going to fund my PhD. And so thanks to them, I could continue and do my PhD in Edinburgh. And so, I was getting funded to study all this cool stuff on condition that I was going to come back to South Africa, the country I wanted to be in, afterwards, and work on the stuff I think is cool. So it was a pretty tough deal to go with. But I did that. When I finished my PhD, eventually, I came back to the CSIR, and there I joined MIAS, which was the Mobile Intelligent Autonomous Systems Group, where I dived even further into robots and trying to get robots to do interesting things. We'd hack together some hardware. Well, other people would do that. I'm not an engineer, so I'd watch other people hack together hardware, and then I'd go and look at what the software was up to. And while I was there, I kind of discovered that I think I was an academic at heart. They actually called me the token academic in the group. So I was always interested in supervising students and writing papers and that sort of thing, not really the engineering-y type stuff. And so I took up a visiting position in computer science at WITS at the same time, where I started a robotics course that we still teach to this day with a colleague of mine, Pravesh, who'd helped me with my first-year subject choices all those years before. I also started the RAIL lab, the Robotics, Autonomous Intelligence and Learning Lab. This is a picture of us from a few years ago. I think there might even be some of these people in the room right now. And I had this realization that we weren't really doing the research in a right way here. The culture was kind of wrong. We didn't have labs. We weren't meeting regularly. We weren't pushing ahead on big projects. And we weren't publishing in the right kind of places. And I realized that having spent time in another lab, there was something wrong with the culture, and I was determined to try and and work on this. I wanted this to be a really fun, exciting place to do research in the kinds of areas that I cared about. And I always said to myself, I wanted to make sure that nobody would ever have to go abroad to study machine learning ever again. Of course, they could, and I'd help them do that, but I'd love it if they would stay here. And I'm really excited that in the last few years, several of my top MSc students that could have gone anywhere have chosen to stay at WITS and stay in our lab and work here, which is really exciting. So in 2019, I then joined WITS full-time, and here we are. So my lab now has several academics, and we've spun out other labs from that. There's on the order of over 100 postgraduate students, and I think we're doing a lot of really exciting stuff that I'm really excited about. And that's what I'm going to talk to you mostly about today. This was just the prelude. So what we actually work on are these guys. Well, not really these guys. Intelligent machines. This is just a cute caricature of one. Right, I really want machines to do cool and useful and helpful things. But doing cool and useful and helpful things means working alongside people. Right, this is just a core ingredient of it. They don't exist in isolation. They exist as part of a bigger system. And so this is really what I care about. How do we build these kinds of machines that are just maximally useful, that can help us build the kind of societies, the kind of lives that we want to build? And the way I think about this is that there's three factors that we need to pay attention to if we want this to be the case. Firstly, we want our systems to be flexible, in that we want them to be able to do a lot of different things. We'd like them to be instructable, and this really goes to the heart of working alongside people. We'd like to have some easy, intuitive way to communicate with our machines. And finally, it should be reliable. If I tell it to do something, it should do the thing. Now, looking at the first two here, this really talks to the generality of machines. There's a long history in this field of trying to get a machine to solve one problem and one problem only, and I find that somewhat uninteresting. I want this kind of general purpose machines. But alongside that, we need to pay attention to safety, which is becoming an increasingly big deal in the AI community this year, really. And so these are the key principles that we're going to follow. And in this talk, I'm going to first talk about the machine side of things, and then I'm going to talk about the people side of things. Okay, so let me give you kind of example of what I have in mind. Let's imagine we have this simulated office environment where I've got my robot, and I want it to do a whole lot of different things. So I might ask it to do the following. What I want to do is go pick up mail, because for no apparent reason, there's physical mail in this building that has intelligent robots wandering around. Having picked up the mail, go deliver it to the people who need it in the other room. And then all the other people are sad because they didn't get any archaic mail. So take them all coffee. And then I want you to patrol between these locations 1, 2, 3, and 4 until you need it elsewhere. But while you're doing this, try not to bump into any of these decorations and break them because they're very expensive. So we bought these expensive decorations, probably in the mail. And this might be the kind of complex task that I give my robot. Now, I want to be able to deal with these robots, right, so that they can solve this wide range of tasks in a human-specified way, and so that I can kind of verify that it's going to do what I want it to do. Now, this is different to other kinds of machine learning. Right? Everybody suddenly knows a lot about AI and machine learning. That's been the joy of 2023. What was once a niche thing is now a I told you so. And there's a couple areas in machine learning that people tend to spend a lot of time. The one is what we call classification, trying to determine if something's a cat or a dog. I couldn't for the life of me get ChatGPT to get this hand to point at the cat. It's ridiculous. Anyway. So this is classification, trying to identify does something belong to one class or another. Is this a face in an image? Is it a cat or a dog? And so on. And of course, the other area is the kind of ChatGPT large language models that generate a lot of text. This is a very different kind of problem to these. And while I'm probably going to talk way too long today, I don't have time enough to go into these differences, but hopefully that'll come up as we go along. So I work in this area called reinforcement learning. And what that's all about is the interaction between a decision maker, which we call our agent, and the environment, the area that it exists in. So we have our decision maker and we have our environment, and we want to be able to solve problems in there. And as I said, these problems could be walking across the space, but they could be picking up mail, they could be making coffee, they could be any of a number of things. And this interaction kind of works as follows. Our agent gets to choose actions that it can take at different points in time. This might be moving a leg or an arm or opening a door. And as a result of the actions that it takes, the state of the environment changes. And the state could be the position of the robot, it could be whether it's holding something, it could be if the machine's on. So there's kind of this interaction between the two. And finally, our agent gets some what we call reward, which is some feedback that tells it if something good or bad is happening. 1 second, please. Now, what this really looks like is, let's say we've got our little robot living in a very simple world like this. The states might be that the robot could be in different places. It might be if the door's open or closed, and so on. And it could be other complicated things like, you know, where are the other people in the environment? What am I holding? Various other things. We could have a set of actions that the agent can choose to take. So maybe move left or right, open the door, close the door, pick something up, and so on. Or it could even be to move by different angles, its arms and legs. We then have this idea of transitions, which says if I'm in a state where it is now, and I choose an action, then something happens. So in this case, if it chose to take a step to the right, then it moves to the right. Right? This is how its actions affect the world. And finally, we've got to care about something we call the reward function, which is when are good or bad things happening. So in this case, maybe you get a reward of +10 for getting the present, or -3 for falling in the hole. And these are all the elements we need to care about to model these problems to get this agent to make decisions. And again, the decision here involves taking multiple steps. These multiple steps are what we call a policy. And so a policy or a behavior might be, in this case, move right 4 times, then open the door, and then pick up an object. What we really care about is the optimal one. Now, the optimal policy is the one that's going to get us the most rewards. But we have to learn to do this through trial and error. I'll show you this in a minute. And with this limited feedback. So it might move left and right for a while and not get any feedback until it falls in the hole or picks up the present. And this makes it a difficult problem because it doesn't really know always what caused the good or bad things to happen. So let's talk about these rewards. The rewards are just a number. It's like that +10 for getting the present. And these really encode things we do or don't want our agent to do. Right? So maybe we'll give a reward of +10 for winning a game, or -100 for crashing a car, or give it some reward for speeding, or for getting or negative reward for speeding, or a positive reward for solving some subtask of a problem it's trying to solve. Right, so it's kind of finicky. We have to set these numbers with all the things we do or don't want. Right? And then this is difficult for the agent because it gets these after a long time, it doesn't get them all the time. But as I say, the problem is it's difficult for us to set it. We've got to figure out exactly what it is we do or don't want our agent to achieve. Now, anyone who's worked in any kind of environment with people knows that it's very difficult to incentivize people properly. And these are things that are good at optimizing. So what do I mean by that? Well, as an example that I happen to really like, back in the early 1900s, in colonial Hanoi, there was a really bad rat infestation. It was so bad the government didn't know how to deal with it. And so they used an early form of crowdsourcing where they said, okay, let's see if we can find a way to get the population to take care of the rat problem for us. So we'll pay people for killing rats. But obviously we need proof that they've killed a rat. We're not just going to take their word for it. But we're also not idiots. We don't want rat corpses piling up in government buildings. So just bring us a tail as proof that you've killed a rat. So that sounds like a great plan. That's a good incentive structure to go for. Only what did they find? Not only did the rat problem not go away, it got worse. And now there were considerably more rats running around. None of them had tails. It turns out breeding rats and cutting off their tails was a good source of income. And so setting these incentives is quite a challenge, particularly for a machine that is going to optimize whatever we tell it to do. Now, machines can't just rely on these instantaneous rewards. They've got to look further ahead. If they do, if they're just going to act based on what's happening immediately, that's what we call being short-sighted or acting myopically. As an example, let's say I had this robot over here, and it could take one step to the left and get some payoff, or one step to the right and nothing happens. So the obvious thing to do is you want to go to the left, but it might be that going to the right, nothing happened because you had to go a few steps further and you'd get a huge payoff. And so the point is we can't just make a decision based on what's going to happen next. Maybe we do this if we're politicians or something, but generally if we want efficient decision making, we've got to think about the effects of our actions into the future. So we get around this problem with, I think this is the last bit of terminology I'm going to introduce, something called value. We need to know how good is it to be somewhere. You know, if you look at this picture, there's this notion that it's a bit better to be one step to the right, but even better to be 2 steps to the right, and even better to be 3 steps to the right. This is what we call value. And if we could kind of learn this or work this out, that would help our agent being able to make good decisions. So it looks something like this. If my agent was just walking around this environment, getting no feedback, and finally got to a present, maybe at that point it gets a reward of 100. But as I said, that means the whole time getting up to that point it had no feedback whatsoever. This is really difficult to learn with. And so we can think to some notion like the step just before that maybe was worth 99. It was kind of close to getting 100. And the step before that maybe 98. It was a little bit further away, but there's still some value associated with being there that's, say, higher than being a couple steps further. And so we need this notion of value to be able to decide what we should do at any point in time. Now, how do these agents learn? Well, typically they don't know how the world works. And so, unlike other areas of machine learning where we give them huge data sets, here our agents have to walk around and gather data themselves. So it might be over here and decide to go north, it moves there and nothing happens, or it gets no reward. Or it's somewhere else, it tries to move north, it can't move because it bumps into a wall and gets a negative reward. So it's got to generate this data itself to learn from that. As it's learning, as it's moving around and learning, it's storing this information in this value function. It's trying to estimate how good is it to be anywhere and do anything from there. And finally, we're going to use this to help it decide what to do. And so what you see here is that our agents, while they're moving around and trying different things, they're learning as they do that. And this makes it inherently a different kind of machine learning to the other popular kinds like classification. So as it does this, as it moves around the environment, we ideally see it getting better and better. So you can see this graph improves to the right. That means the more times it's spending in the environment, it's bumping into things, it's moving around, and it's slowly learning this value. It's learning how good these different places are in the environment. And this is how these kinds of agents learn. This is how we get our robots to learn, which is great. But the problem is that the world is large and complicated, and it takes a very long time to do this. So if you're trying to walk around a simple grid and pick up like something nice at the end, that takes a while. But if you want to make pancakes, you're going to be there forever with pancake batter flying all over the ceiling. Right? It's learning from trial and error. It's got to get all the things wrong to be able to figure out what to do, which is not ideal. I don't want my autonomous car driving in this kind of way. So this is the first big problem, is that learning is slow. We also kind of know this as people, that we're kind of useless for the first couple decades of our lives while we learn to do things. But a big challenge in the field is typically, if you want to learn to do a whole lot of different things, you've got to learn each one from scratch. And this takes a lot of time. This is no good. And we have to be able to transfer knowledge between different tasks to be able to solve new tasks faster. And this is one of the core challenges that we look at in my research lab. So I'm going to take you through just a small subset of the kinds of projects we've been thinking about to see how we get around these kinds of challenges. So it started back during my PhD, where I thought, okay, let's say you're a robot and you've got to interact with a person. You can't learn your whole interactive behavior from scratch. I mean, imagine like a chatbot that was just learning how to speak with you the first time it bumps into you. Right? It would be the most irritating experience of your life. So instead of maybe learning a behavior when you're actually interacting with someone, maybe you can select one from a set of behaviors you've encountered before. And if each of these are tailored for different kinds of people that you might have encountered before, then instead of learning a new behavior when you encounter a new person, what you've got to do is select the best one. And so we came up with a framework where we could, based on some very limited interactions with a person, try and choose the best behavior for your next interaction. Now this, in later work, built out with a PhD student of mine, Jean, who is at TU Berlin, and we showed that we could use this kind of thinking to get a robot to anticipate what a human's doing or what a human might be struggling with, to choose the best kind of response behavior to help them with their task. And we could show that after just a handful of interactions with a person, you could learn exactly how this person works by mapping them to which people that I've encountered before do you look most similar to. So this was really cool, but it required you to interact with a person to learn a bit about them, to update your estimates. Right? So it's helping you respond to tasks rather than learn to solve new ones. So I wasn't very happy with that. That wasn't what I was looking for. So we tried some other things. This was another project during my PhD where it was based on this kind of intuition. Imagine you're walking along and you're at this intersection in the middle of this little world. And you've had to solve some problems before in your life, and a couple times you solved them by going north, and maybe you once solved it by going to the west. You never went to the east because there's a terrifying monster over there. Now, from those 3 previous experiences, maybe something I could infer from that is that if I found myself in that situation again, and I don't really know what I'm trying to achieve, a reasonable thing to do would be to maybe go up 66% of the time and go to the left 33% of the time. And just use my previous experience solving different kinds of problems to solve a new problem faster. And in fact, that's exactly what we found. We found that using this kind of methodology, as you solve more and more tasks, you're able to solve completely new ones considerably faster, right? Without doing this, you'd be acting like this red line, but now you can act like the green line, which is very cool. Take my word for it. Okay, so this was really exciting and showed that there are ways that you could bring this knowledge across between tasks to solve new tasks faster. Now, this opened up a whole lot of other avenues that we've looked at, and I'm going to talk about work that I've done with various students and colleagues, and particularly this is work that I did with my then student, Steve James, who's now one of my closest colleagues and partners in crime for running horrible machine learning things around here. And during his PhD, we looked at this idea that something that might be useful across trying to solve a whole lot of different problems is a skill. Right? I don't need to learn to solve I might need to learn to solve different things, but there's generally useful skills like opening doors and picking things up. And if I can learn not just these skills, but when to use them, then that's incredibly important. So, for example, in a little video game setting, I could learn a skill to climb down a ladder. But not just that, I could learn that it's useful to use this when you're standing at the top of a ladder, and the effect of it is you're now at the bottom of a ladder. Now, this is really useful because then if I'm encountered with a completely different problem, all I have to do is find the places that look like the top of a ladder, and I know what I can do in those situations. So then I'm able to piece together all these skills and when and where I can use them because I know what the effects are going to be and be able to solve really complicated problems. Right? So here we've got this agent that had to climb down from the top and go get this gold statue and open doors along the way. And it's able to do this because it understands all these different mechanisms of how to pick things up and open doors and navigate ladders and staircases. Right? So I can do this now with minimal learning. It just really has to learn where can I use these different skills. We even managed to, for the younger ones in the audience, use this to solve complicated assembly tasks in Minecraft, where you could wander around and pick up objects in different rooms and construct things. There's other kinds of structure that you can learn when you're trying to solve a whole lot of different tasks. This was work that I did with another PhD student, Ophir, who I saw somewhere earlier, where instead of learning about your skills, maybe you can learn about how things in the world interact with each other. Let me show you what that means. So this is a little game called Sokoban, where you've got this little character and you have to push these boxes around and end up pushing them onto those green dots. And this is quite a difficult game because you can end up in situations where you've backed yourself into a corner and and can't solve that. But there's a few simple dynamics that you can learn. You can learn, for example, that if I'm trying to push a box and there's nothing on the other side of it, it can move. But if I'm trying to push a box and there is something on the other side of it, it won't move. And we showed that you could learn really simple, really efficient rules, explainable rules that you could basically read out in English. You could learn them from a simple level like this, and that gave you enough knowledge to be able to solve considerably more complicated problems like this one over here with 4 boxes. Which gives you this kind of idea of learning from a curriculum. You can learn everything you need to in a very simple, quick setting and transfer that to a much more complicated problem. Now, in addition to thinking about these kinds of transferable bits of knowledge, there's another big challenge, which said earlier, defining tasks is difficult. Right? This comes down to setting those reward functions, choosing that this is a +10 and that's a -1 and that's a 2.3. And if you get this wrong, you get really weird behaviors coming out of your agents, which is a thing we really worry about in the field. You need a lot of expert knowledge, and you've got to make sure you don't end up with tailless rats running around. All right, so how would you even go about setting those numbers to solve a problem like this robot trying to deliver the parcels and coffee and everything? Is there a more natural way to define these tasks? So asking this kind of question gave rise to a whole lot of different research projects with a whole lot of students. And we're building some really exciting stuff now. So what I'm going to talk about here is work that's largely been driven by my PhD student, Gerard, from his master's and his PhD, where we're trying to ask these kinds of questions. I want to be able to ask to specify tasks that are human understandable, such as do X and Y simultaneously, or do X until something happens and then do Y. And we also want this to be theoretically verifiable, right? That it's definitely going to do what we want it to do, because that's quite important, right? This is how we get safe and robust behavior. So let me show you what I have in mind here. So this could be the environment. We've got a little character. You can wander around and pick up different kinds of objects. Be boxes and circles of different colors. And I could learn a behavior that says this is how you pick up blue things. So I could spend a lot of time learning how to do that. Then I could separately learn a behavior that says this is how you pick up boxes. This is how you find the closest box. And the question we wanted to ask was, can we compose those 2 pieces of knowledge to solve other problems that are built out of those pieces? So for example, I might want to be able to say, pick up something that's either blue or a box. Can we do that based on this knowledge? Now, the standard frameworks for doing this don't let you. There's all sorts of technical challenges. But we found a way. We found a way that says if you've got some environment, you can define these internal goals, these things you might care about, a different way of structuring the reward functions. I won't go into the details here, but with some small tweaks to the way we set up the problem, this lets us solve for what we call a world value function, which is this kind of knowledge, this value function, this behavioral knowledge that tells you something about all the things you might care about. Without going into too many details, what this means is that if I've spent some time learning to solve 2 problems, let's call them A and B, then I can get solutions to other problems coming out of that, particularly the solution to the problem A or B, A and B, or not A. And I'll show you why this is important in a second. What's important is I get those solutions with no additional learning and in a way that's provably optimal. So if my little ant here has learned how to get to the bottom left and separately has learned how to get to the top right, I could say, go to the bottom left or the top right, and it doesn't have to do any extra learning. It just gets this for free. Now this is important because this and, or, and not gives us something called a Boolean algebra, which is a really important kind of class of, or structure of mathematics. And it turns out what that means is if I've been able to solve some number of base tasks, these A's and B's, my robot, my agent gets a super exponential set of capabilities based on that. So if I've just solved 10 base skills, 10 of those A's and B's, then without doing any extra learning, I can solve some obscenely ridiculous number of tasks without doing any extra learning, which is incredibly powerful, right? So given that to pick up blue or boxes, I could now say, get something that's blue or a box, and there's the solution right there. Or get something that's blue and a box. Or something that's not a box. or something that's either blue or a box, but not a blue box. Right? And I can start specifying these things in a very human-readable way and be guaranteed to get the solution that I'm looking for with no extra learning. None of that extra waiting for my agent to grow up. So we've done all sorts of other interesting things with some collaborators. We've even managed to plug this into large language models. The one I'm showing here wasn't ChatGPT, but we've done that too. So I could give it an instruction in natural language to say, pick up the red ball. And this gets translated into these Boolean expressions and turned into a behavior. And even gets better as we give it more and more tasks. We end up with behaviors like this. So we can say, go to the green chair or go to the red sphere that we specify in English, and it will do the thing for us. Right? In this really complicated environment that would take ages to learn in otherwise. And I was particularly excited when we managed to pull this off on a robot, because I think that's a sign of a machine learning research lab growing in maturity. And so here what I'm going to show you is some experiments we did in our lab. We got our cute little curry robot to learn some base skills. So the one base skill was to go to the bottom, and it learned how to do that, which took ages. Another one was to go to the left, and it learned how to do that. But now I could get it to solve these combinations. I could say, go to the bottom and the left. Didn't have to do any extra learning to do that, and it can pull it off. Or go to the bottom and the left, not using the door. Okay, I didn't use the door last time, but generally if I changed the way of specifying the instructions, I'd have to change something and relearn. What about go to the bottom and not the left? And then finally go to the bottom and not the left and not using the door. So instead of me having to specify all these numbers of what do and don't I want, I can give it in this very interpretable set of instructions, and will solve the problem for me with no additional learning. One of my master's students, Simon, then showed that we could even use this in multi-agent settings. So in the top left there, we can see that there's a green robot that has to go anywhere, and the red robot has to go to the bottom. Then in another case, we have to get the red robot to learn to go anywhere, and the green one to go to the right. And then we can ask it to do those two things together, and they even learn how to coordinate. Well, they don't even have to do extra learning, they just coordinate naturally to be able to solve the problem. And we've now tried to look at this in more manufacturing type settings. So a master's student of mine, Jesse, has been looking at this case where we've got a robot that's trying to learn how to pack or unpack these different bins. So I've circled them over here. There's a red bin and a blue bin. So the two ones at the top, it's had to learn a skill to fill the red bin or learn a skill to fill the blue bin. But then the ones at the bottom, it's just composing these. So the bottom left, it's saying, I want the red bin to be empty, and the one on the bottom right, it's saying I want either the red bin full or the blue one, but not both. And so it can compose based on just having learned these two skills to solve a whole variety of different manipulation type tasks, which hopefully the next stage will see us building Lego structures from this. And so you can see you could give these arbitrarily complex instructions, and it's just piecing together the bits of knowledge that it's learned separately to do that. Okay, so now if we remember what our motivating example was, I want the robot to be able to do these kinds of things. And there was something fundamentally different about this problem, which we have to be able to reason over time. I want to do something, and then do something, and then do something until something else happens, and then do something, but not something, and you know. So this framework we've developed doesn't really support this. So we had to take this a step further. And again, this has been work that Gerard's been pushing on, where we've been looking at, instead of looking at these Boolean algebras, can we look at what we call, well, we don't call, everyone calls, temporal logics. And this works as follows. I've still got my environment, and I still need to learn some basic skills there. But I want to be able to specify something in an LTL, which is a type of logic that specifies these time relations. Do something and then something else. There's a whole kind of framework that we built that translates this into a way of expressing the rewards and synthesizing behaviors and letting us solve the problem. I'll show you some examples of this. So first, here's an example which says navigate to a button, the little orange thing, and then to a cylinder. So we can just specify as in a very neat mathematical notation. We've never had to train to do this task specifically, and then it solves this problem. or something else. Navigate to a button, then to a cylinder without entering a hazard region, that's the blue circle, then to a button inside a hazard region, and finally to a cylinder again. Or navigate to a hazard, then a cylinder, and finally to a cylinder again, but avoid hazards while you do that. And so I can specify all these different kinds of tasks, this whole zoo of different tasks, and I don't have to do any extra learning for any of them. If I've learned about all those base components, the solutions just fall out when I ask for them, which is quite remarkable. Particularly because I can say don't do certain things, avoid certain things, and this is bringing in this whole aspect of AI safety, which is critically important. So now we finally have everything we need to deliver the mail, then deliver the coffee, and then do the patrolling, and not bumping into any decorations. And so this was the solution to the problem that we cared about all along. Get a robot to go in one by one, deliver the mail by using these temporal logics, so we can just specify the task descriptions as we've described here, deliver everyone else coffee, and then finally do the patrolling, and the whole time it's avoiding those green objects. So these are the kind of frameworks that we're building in our lab here. We're looking at the fundamental science of decision making and how to build these kinds of frameworks to enable faster, more efficient, and safer decision making in autonomous systems. But that is only one piece of the puzzle. The other is the people. Right? We're building these machines to exist in a world that's already inhabited by people. So with all these amazing frameworks, you can ask the question, are these three principles enough for us to kind of safely and successfully deploy all of these technologies anywhere in the world? And I would argue no. You know, think about a bit of a caricatured situation. If you've got a car driving down a road in the Pilanesberg or Philadelphia, right, there's a few things that might be different. You might use different words to refer to things in different languages. Maybe stopping at the bend in the road would mean a much smoother drive in the one than the other. One, you maybe have to avoid pedestrians, and the other elephants, and these are very different concepts you wouldn't even need to know about in the other setting. What is even permittable? In some places you can drive on one side of the road, in others you're kind of encouraged to. Works a little bit differently in different places. Even the driving behavior itself, whether it's 2x4 versus 4x4 or other kinds of driving behaviors, this is going to be very different depending on where you drive and how you want to work. Right, the example I love to give is if you give someone the instruction, turn left at the robot, right, a foreigner is definitely thinking of that. And we're definitely thinking of that, which is an important distinction to bear in mind. So what this means is we need local experts. As we're pushing AI out into the world faster and faster with all the craziness of the last year, you know, we need to make sure that we understand the local languages and context, values, priorities, challenges, right? There's a lot there that's particular to different places, right? We need local experts in algorithms, in software, in hardware, linguistics, ethics, policy, and countless more. We need communities. Right? And we can't successfully embrace AI if we don't have communities. These are quite difficult to build. I can tell you this from what I'm about to tell you. So when I came back to South Africa, there was not a lot going on here in the machine learning space. I was working at the CSIR, and I was in touch with a few colleagues, locally and abroad, and we were discussing this a lot. And in 2017, a group of us decided to come together and do something to strengthen machine learning in Africa. This started with a person I've mentioned a few times in this talk already, George. We'd been co-supervising a student together, Pravesh. And we'd often chat about these things, and there was someone he'd been talking about a lot, Ulrich, who was a South African working at DeepMind. He said, no, he has to put us in touch with each other because we both care about these things. And it was in January 2017. He sent an introductory email. A few days later, we had a call with a few other people, and we decided that year we're going to start a summer school. We're thinking about trying to bring one of the major conferences to South Africa. We thought that wouldn't make sense, all these academics parachuting in, leaving, and there'd be no value to the local community. That wasn't any good. So we decided to start something. We thought, let's put together a small summer school. It'll be a few days. We called it the Deep Learning in Indaba. And the idea was to make an intense, state-of-the-art machine learning workshop for African researchers. Right? Just a few of us organizing it. We'd kind of fund it ourselves. We'd give all the talks. And there's probably only 30 people who would be interested. So this is a particularly unflattering photo of the founding committee, the 8 of us who put it together. There may or may not have been drinks involved that night. But we decided to host the first event. We held it at Wits University in August that year, 2017. And it was a bit of a hit. In fact, we went on and held many others. That was our organizing committee the next year. And at the moment, our organizing committee is about 70 volunteers from across the continent. So what happened? Well, that first year, we held this event, I think it was 5 or 6 days at Wits. We had 330 attendees. We had about double that in applicants. So we realized there were things going on here. We needed to kind of find ways of spreading beyond just the people who could attend. We needed funding to help us bring people here. We ended up having to raise a lot of money to kind of fly out students. We made this very broad. It was open to academics, to students, mainly masters and PhD, but even some kind of late undergrads. There were people in industry and all over the place. And there was just so much momentum and so much drive for this that we kept going. The next year we took it to Stellenbosch. We had 550 people. We then took it to Kenyatta, and we had 700 people. We took a bit of a COVID break, and then we came back and went to Tunisia for 600, and a few weeks ago we were in Ghana with 800. This has become a huge, vibrant, thriving community. I mean, these are the numbers of people that have been applying every year. And it's just been crazy. You go to this event every year, and there's new people, there's some of the old people, but people from all over Africa that come together and they're hugging each other and asking how their research is going. I've literally never seen that happen, except maybe sports people or politicians knowing each other from other countries, which was mind-blowing that we don't have these connections. It's not a common thing that just be people working in industry, with startups, with studying that know each other across the community. So the way the Indaba Week works is there's a lot of these big keynote lectures, and we often get big names to come out. We've had all sorts of interesting characters come and speak. We have practical sessions, the deep dives into the technical kinds of concepts we think people should be learning. And we even have parties, because what's a good conference without a party? But what we found, even from the first one, is that it was critical for us to make it accessible. Being academics, we go through a double-blind peer review for everyone who applies, and we'd have a number of people that would email us from Ethiopia and say, "Thank you for accepting me. This is the greatest thing that's ever happened to me. Unfortunately, a ticket to South Africa is 5 times my father's monthly salary." And so we went to great lengths to raise a huge amount of money to be able to fund many of the students, give them scholarships. No students would pay for their registration. That was all about industry. And so we built up on this momentum, and we kept growing this. We kept innovating. We kept trying new things. And we've tried many experiments over the years. We now do an Africa Research Day, which is one day where all the attendees are presenting posters on their own work. It's not just about foreigners' work. This is about African work as well, and African excellence. We have a lot of parallel tracks now. There's sometimes ones that are intro sessions versus deep dive technical sessions versus things on policy versus things on ethics and so on, all happening at the same time. We have workshops that attendees can organize themselves. Many of the members of my own lab have organized workshops for the last couple of years at these events. We have events for women in machine learning, and even there we push hard to make sure, I think we're currently sitting at 40-something% of our attendees are women. We have sessions on ethics and startups, and sessions on how to write good papers and apply for PhDs and all sorts of exciting things. It's really just become this vibrant community of people pushing each other forward. We've been very much driven by kind of a few core principles, right? At the heart of this community is this annual summer school. But we had a bit of money left over after the first one, and we thought, what could we do with this? How do we expand the reach of what we've been doing? And we started a program called the Indaba X, which is to have satellite events in other countries. But there was no point us running that. We don't know what works in a different country. And so we encourage local organizers to put their own event together. We give them some funding, help them with some logistics. And at the moment, we're running these we're not running, we're supporting these in 36 African countries. This is the community of machine learning summer schools. These are all the places that have active machine learning communities, and we're now working to try and bring the other countries online that haven't done this yet. We also have a number of other things going on, like awards programs. We've tried to encourage, recognize excellence in the community in all sorts of different ways. And we've really been pushing this. So between the Indaba X's, we have several thousand attendees coming through those events every year. So it's become a massive community that's just kind of driving change across the African continent in a very unified kind of setting. We've even tried to take this further abroad. Members of our founding committees have helped everyone from the Eastern European Machine Learning Summer School to the Southeast Asian one to the South American one, help them try and build similar kinds of mechanisms based on the success that we've been having here in Africa. And the impact has been huge. So there have been a number of papers coming out. In fact, when we started this, one of the first discussions we had was that in the flagship machine learning conference called NeurIPS, there'd never been an African institution represented there when we started this in 2017. And now every year there's a few. A lot of people, I've supervised students across the continent that don't have supervisors locally. There's a number of people that are now studying abroad or in other countries that haven't been able to do that. There's new startups, there's new jobs. There's this huge international collaboration network, and the whole international machine learning community has jumped on board to support this and offer mentorship and all sorts of things. There's new courses running everywhere from here to across the continent as well, and new programs. And there's even new VCs bringing funding in to support the work that's being done in AI and machine learning across Africa. And just to show you one thing quickly, about a year and a bit ago, myself and 5 other crazy people decided we'd start our own startup, Lalapa AI, to try and build AI for Africans by Africans. We now say we're building the best language models in Africa. We're building language models for all the languages that are underserved by all the work that's being done in the West. Right? All of the ChatGPTs and those kinds of things do not serve the 2,000 African languages that we have on this continent, and where they try to, they're very bad at it. And so we've taken this as a personal challenge that we're building this up and showing that Africa can do these things as well. And so with that, I want to just start tying everything together. What I really care about, as I've been saying, is about building intelligent machines and building intelligent communities. Right, we want to build an amazing world where we've got human-machine collaboration, machines helping us build all the crazy things we're trying to do. And I think there's these 3 key principles that really build us towards general agents that are safe, right? We want them to be flexible, we want them to be instructable and reliable. And that's absolutely critical, to think about new frameworks, to build new frameworks, which is what we try to do here. But we absolutely cannot forget the piece about community and make sure that we're building human-human collaboration at the same time to really build the world that we care about. I just want to leave you with a couple key takeaways. It felt like a very inaugural lecture thing to do. The first thing I would say from my journey is do the coolest things you possibly can. Always do the coolest things you can with the coolest people that you can. It's been my driving philosophy in my research. And amazing things happen when you build together with other people. Don't do things alone. If you're struggling with a hard problem, you tend to think you're an idiot. If you're struggling with a hard problem and you're working with someone else who you think is super smart and they're also struggling with a hard problem, then maybe you start to tell yourself, okay, maybe this is a hard problem, right? So you've got to build together. And the important things there are you need critical mass, and you need the right culture and the right attitude to what you're doing. You need good support, and you need what's in 1A, the coolest people possible. Many projects and ideas fail, and you must learn from each one. And don't let a no stop you. Whether that no is an MRI, or not getting funding to do your PhD, or even some research ideas that don't pan out, or you think that the rest of the community is doing it wrong. Don't let that stop you. Try something different. Do the thing you think is the right thing to do. And finally, I just really, truly believe that Africa is an incredible place, filled with incredible people, and that motivates me every day. That's why I keep coming to work every day because I don't know how you could possibly be pessimistic about the future if you get to, say, work with the students that we have here at WITS every day. That just really drives and motivates me. So I've got a few thanks I have to give. Firstly, thanks to my lab and all my students, and many of them are here, thanks guys, for all the amazing work that you do. None of this would be possible without that. Specifically, thanks to everyone who helped on these projects that I spoke about today. This is just a small subset of the projects we work on. I could have given a very different talk with a completely different set of projects, and that's just really so exciting. And then, really, thanks go out so much to pretty much everybody here and so many other people. Thank you to all my family, friends, mentors, colleagues, collaborators, funders, and students. Probably covers everyone in those groups. Every single one of you has played some sort of important role and inspired me in some way. Mostly, thank you to my awesome, awesome wife, Oni, for all her endless support and dedication and bringing me tea or coffee or whatever it is I need at any hour of the night, and then bouncing around the craziest, strangest ideas with me and telling me I'm not quite as crazy as I think I am, and usually giving me better ideas anyway. Thank you so much for everything. And thank you to my family who have been supporting me while I was a very, very difficult baby with a hole in my head all the way through to a very, very difficult professor with a hole in his head. So with that, thank you everyone. Thanks for your attention, and thanks for coming.
Benji, that was absolutely superb. Really presented your ideas around artificial intelligence without giving us a single piece of code. I think we sure appreciated that. Pictorially, you certainly communicated the ideas very cogently. I think the audience has appreciated that. What a wonderful audience today, and I want to recognize our Vice Chancellor who walked in, Professor Vilakazi, who I know is extremely keen on driving ideas around artificial intelligence and machine learning, and you could see these ideas are really at the very cutting edge and developing very rapidly. So thank you very much for sharing your story, but especially your personal story, and that was very touching. So colleagues, it's my pleasure then to call upon, well, we're going to keep this in the family then. It's Dr. Kevin Rosman, that's Benji's dad, who's going to be saying a few words of thanks, a vote of thanks then. Just a few words then. Dr. Kevin Rosman qualified as a medical doctor in 1976 from the University of Pretoria. He then qualified as a neurologist in neurology in 84. There was a master's in medicine, and then a doctorate in medicine in 1990, both from the University of Pretoria. In 2000, he was awarded a fellowship of the College of Neurology of South Africa by peer review. He has been in private practice as a neurologist since 1987. He started the first private sleep laboratory. That must have been quite nice to be a subject in there, in South Africa in 1992, and has been involved in sleep medicine since then. He also started and served as the president of the South African Sleep Association. He served as an honorary lecturer in neurology at both WITS University as well as the University of Pretoria. He semi-retired in 2021. Ladies and gentlemen, it is my pleasure to call upon Dr. Kevin Rosman to propose the vote of thanks.
Difficult act to follow. First of all, Professor Osmond, Professor Chetty, Professor Klein, Justice Cameron, all the other distinguished guests, ladies and gentlemen, thank you firstly for the privilege of letting me be here and offer this vote of thanks. Now, we've just seen a very practical example of what happens when a very complex electromechanical computer, that is to say a human brain, is born with a very large hard drive and powerful parallel processors. Will we get there with artificial as opposed to natural computers? Well, time will tell, but we've just heard from one of the class of people who's going to make that happen if it's going to happen. I'd like to take you back a few years, particularly for those who are a little younger than I am, to emphasize how far we've really come in the world of computers under the tutorship, under the leadership of people like your newly minted professor. When I was at school, we were told with complete certainty that computers would never play chess. When I was at high school, we had an optional subject called computer science. Now, this actually didn't involve using any computers because we didn't have any. There were very few around. So we had to sit and learn to write programs on paper, and it was very hard to actually check that what you wrote did anything. In my first year at university, we did statistics, and these calculations had to be done on an adding machine because there weren't any computers other than expensive mainframes. When I had to do some correlations for my PhD, they had to be done on the mainframe of the Medical Research Council because other things just couldn't take this amount of data. When I was a lecturer, my head of department came to me one day and told me that the university was giving the department a computer. And he said there's no way he was going to learn how to use this thing, so he dumped it in my office and said, do things. I stood and looked at it and hit a few keys, and nothing much happened, and I couldn't get it to do anything. And this thing had 2 drives. And then I discovered that you've got to put a floppy with a program into one drive, and you put another one with the data into the other drive, and then you can make it happen. Now, these programs are very, very advanced, you must imagine. The program for writing, equivalent of Microsoft Word, I suppose, the instruction manual was all of 10 pages in big print. It wasn't even a full scale, little pages. So for those of you whose memories are not that long, that's where we came from just a few years ago. At home, we were early entrants into the computer area. And we managed to get hold of a BBC computer. The BBC, that's the British Broadcasting Corporation, they sponsored making a computer, which was really cool. And this thing had all of 32 kilobytes of memory. But what was really nice about it, if you wanted a program, you bought a little chip with it, and you opened up the computer and you plugged it in, and then you had your program on the computer. What was really good about it is that the boot up was instantaneous. You press the switch, went ping, ping, and you were in, and everything happened that you wanted to happen. Of course, there were limited programs you could put on the thing, and they weren't very well written. But it also had a color screen and a great selection of programs for kids. So it was wonderful when you've got young kids at home, and you can put games on. There were things like Color Snap, where you've got to match, you've got to hit the button when the 2 shapes are the same color. And quickly mastered this because they really weren't very difficult. Then one day when he was 7 or 8 years old, as kids do, he came along to me and said, "Daddy, I'm bored." So this computer, the BBC computer, had come with a great thick manual for the programming language called BASIC. Now, probably most of you don't remember that. It was very basic, but okay. I sat with this in one of my weaker moments and learned to put 2 dots and connect them with a line. So when he came to me, I took him along, put him in front of the computer and gave him this great big thing and said, "Okay, go ahead." An hour or 2 later, he came to me and he showed me that he could draw a teddy bear. And from that moment on, I have understood very little of what he does on computer. He then finished school and came along to WITS. He wanted to do pure maths, applied maths, and computers. Fortunately, a colleague of his told him that he didn't really need the pure, applied, and computers was really what he needed, so he went and did this. Happily for me, I didn't have to pay for all this, because he was one of the 10 best students entering the university, and he became a Vice-Chancellor's scholar, which meant that everything was covered for his degree, which was really, really great. Then obviously he wanted to go on and do an honours. Now, being Benji, one wasn't enough. They wanted to do two. And he wanted to do them all at the same time. Fortunately, his professor said, now hang on a second, even you're not going to manage with this, but you can do it over 18 months, which he did. Then he decided it was time to go on. He had his heart set on MIT. Now, the problem with MIT was that they sort of combined the master's and the doctorate. That's a 7-year program, but when you apply, you've got to tell them what your ideas are for your thesis. And if you've just come out of an honours, you really don't have a lot of clue about that. So he wasn't getting anywhere there, and he was very upset, and eventually he asked around, and he got into Edinburgh, which at that stage was rated number 2 in the world, interestingly. Now, when he left Wits, we tried to work out 2 master's students in computer science and roughly 10 honours students. When he got to Edinburgh, he found the class was about 150 for the master's students, which was just a complete new experience. But interestingly, only about half of them actually had post-matric maths, which was sort of surprising and made me think that, well, maybe our training here isn't all that bad. So he quite naturally drifted into the AI area because that needed maths as well as all the other stuff. As he was coming to the end of the year, his soon-to-be supervisor for his PhD actually wanted him to come and work under him because he realized that there was someone here that he could work with, he had the right background, he was doing things the right way. Well, funding was again an issue. Studying in another country, if you've ever tried, is really, really expensive. Fortunately, Edinburgh wanted him. So the first thing they did was they dropped the difference between the local fee and the fee for a visiting student. And that's a lot. So that made it possible. And then to make it even easier, the CSIR came along and offered him the bursary with a catch, of course, that he had to pay it back. But I must warn you, there was one big disappointment at Edinburgh. Their gown doesn't have enough red on it. So he finally came back and started working as he was obliged to do. And one day along here, we had this whole discussion of what he was going to do after that. And I said to him, look, you've got a choice. You can either be a big fish in a small pond or a small fish in a big pond. So he thought about it for a long time, maybe 5 seconds, and said, well, I want to be a big fish in a small pond. So he was perfectly happy to stay here. But of course, as you've seen, it really didn't take him very long to turn that small pond into a big pond. So from those 12 or so postgrad students, when he left, he's now talking 100 to 200 postgrad students that have either gone through his hands or are there at the moment. Very proud moment in all this was when he received an application from a student at MIT to come and work for him. And I think that was really a feather in his cap. So at this point, he's always wanted to be back here. He's always been very sanguine about Africa, AI. You've heard about the deep learning in Daba. And this is bearing out his optimism. With his help, a number of his students have been able to study at overseas universities, places in highly respected units. Hopefully, most of them at least will come back. And now here he is, Professor Benjamin Rosman. Really sounds strange. We can only look to see what the future brings for the department and for research at Wits as a whole. So again, thank you to all his mentors, thank you to Wits, great big thank you to Benji for being here after all that and contributing what he does to the academic community. And Thank you for having me here today.
Thank you very much, Dr. Kevin Rosman, for those very inspiring words. Benji's story is really very inspiring story, isn't it? Right from childhood all the way through to his professorship, and way beyond his academic career, he builds a community, and that is just so incredibly inspiring and greatly appreciated, Benji. Ladies and gentlemen, it leaves me then to close proceedings. It's been a very enjoyable evening. Once again, so delighted to see so many of you here to support Benji in this milestone. This is really a very, very memorable event for all of us. So on behalf of the Senior Deputy Vice-Chancellor, Professor Rukhsana Osman, the Head of Computer Science within the School of Computer Science and Applied Mathematics, Professor Richard Klein, Benji, of course, and his wonderful family, I wish to invite you over for some snacks out in the foyer, and wish you good night, of course, if you wouldn't mind rising and do enable the academic procession to leave the chamber. Thank you very much.